Today, let's talk about images. Images that are cute, images that are funny, and images that are awe-inspiring. More specifically, I want to talk about how do computers store images. Now, we take a ton of images from our phone and computers every day. I want to explore this idea of how do computers store images. So if you get to the very end of this really long video, I promise there is something magical in store. We will reveal something extremely magical about computers. Okay, let's begin. Here's what we're trying to do. If we take an image of puppies, how exactly does that image get stored inside a computer? We're trying to build a bridge. Let's figure out how that's done. In trying to answer this question, I began to take some inspiration from Hollywood. So here is an image that I found that was in the movie The Matrix. And here's another image that I found when I searched for computer programmer or hacker, which is an image actually that is generally used in the evening news when they're talking about these subjects. Take a moment to pause the video and try and figure out if there are any similarities in between these two images. You may have noticed that you see numbers like ones and zeros. Well, it seems that Hollywood wants us to believe that computers store images as ones and zeros or data as ones and zeros. Well, in this instance, they are right. The stereotype that computers store things as ones and zeros is actually correct. So this image that you see of puppies inside the computer is nothing but ones and zeros. So how is it that a beautiful image, a beautiful mosaic is just converted deep down into nothing but two numbers? Let's find out. This conversation begins with the image of a cup. Simple image. The reason why I chose this image is because it's easier for me to explain to you with the use of this particular simple image how images are stored inside a computer. I could have taken another image, but I chose this one because it's easier for me to explain it. Let's put a little grid on this image so I can refer to the different parts of the image really easily. All right, so let's think about a word that we've heard thrown around a whole bunch of times called pixel. What is a pixel? Well, I looked around in the dictionary and found that it was made out of two words called picture and element. So a smallest element in a picture is called a pixel. Where is the X coming from? I'm not quite sure. So each one of these little boxes or squares that you see superimposed on top of the cup, that's a pixel. Okay? All right. So this image is particularly has what, 12 pixels as height and 16 pixels wide. So that makes it, you guessed it, 192 pixels. Can you see the top left pixel, the box at the top left where the green arrow is pointing? The computer says this particular pixel is white. So I'm just going to store it as the letter W. All right. Then it moves on to the next pixel and says that's white also, so I'm going to refer to it as W again. And then the next pixel is black, so in this instance, I'll refer to it as B. Does this for the entire row. The computer does this, and there it is. We have a whole bunch of letters that are representing the picture. Once the first row is done, it moves on to the second row, and so on and so forth. So in our journey to figure out how we go from an image of a cup to ones and zeros, we've stumbled upon this idea that an image gets converted into a sequence of letters. All right, what's next? Well, the next thing is this organization called Unicode, short for Universal Code. And what it does is that it creates a map between the letters A through Z, and actually many other characters, and numbers. So it says A is 41, B is 42, so on and so forth. W in this case is 57. And so it basically is creating a map between letters and numbers. And so using this particular map, what the computer does, it says, all right, if the first pixel was W, I'm going to try and remember it as 57. Okay? The next pixel is W also, so it's another 57. The next pixel is B, or black, and that is going to be remembered as 42. So it does this for the entire row again, and for the entire image. And so we are now at a point where an image of a cup was converted to letters, which have now been converted to numbers that you and I can understand. Okay, well, there is one more thing the computer does after the step, which is that it takes these numbers that you and I can understand, the numbers like 57, and puts it through a formula box. And the output from this formula box is basically a conversion of that number to ones and zeros. So 57 is converted to the sequence of zeros and ones that you see on your screen. All right, so essentially what's going on is that the number 57, where you see the green arrow, gets converted to a whole bunch of zeros and ones, and then the next number gets converted, and then the next number gets converted, and voila, what we have is essentially a whole bunch of ones and zeros. So to recap, what we have here is the image of a cup gets converted into a whole bunch of letters. And then those letters in turn get converted into numbers that you and I can understand. And then those numbers get converted into a sequence of ones and zeros. Now here's a question. Why are we doing all of this? Why are we going through the pains of converting an image to ones and zeros? Well, the answer is hidden in this image. I'll tell you the name of this device in a little bit, but it's important for me to mention at this point that when I first figured out what this particular device does, I fell in love. Deep love for what we as a species can accomplish. And this particular device, I think, is in the same vicinity of inventions as the invention of the wheel or us learning how to tame fire. It's called a transistor. This is what it looks like right here. And it works very similarly to a switch. They might as well have called it a switch, but they called it a transistor instead. What it does is that it can either be on or off. It can either have a value 1 or 0. All right, let's connect it back to our image. So if our cup has been converted to letters, which have been converted into numbers you and I can understand, which has been converted into ones and zeros, well, each one of these ones and zeros can be stored inside one of these transistors. Now here's the really interesting bit. What we were able to do is take this transistor that you're looking at and make it smaller and smaller and smaller, to a point where the smallest transistor that we have right now is only 4 atoms wide. What does that even mean? It means that we can fit 1,500 of these on top of a single strand of hair. That's really small. And a lot of these transistors exist inside our computer. So here's a simple image of a computer which has a processor inside of it. It's about 4 square inches. Guess how many such transistors we have inside that space? About 4 billion, folks. We have 4 billion of something inside our computer. So if you take an image like this, an image of cute little puppies, it takes about 400,000 transistors to show that image to us when we look at it in our phone or on our computer. Imagine this, when you ask your computer to show you a picture of something, hundreds of thousands of transistors inside your computer are working to make that magic happen. Now, if that doesn't blow your mind, nothing will. So to recap, I want to say we started with a simple image of a cup. We were able to convert that image into letters. Those letters were then represented by numbers that you and I can understand. And then each one of those numbers was converted into ones and zeros. And ones and zeros can be stored by transistors. And that's how computers store images. So we now know that images on our computer are stored as ones and zeros. I wonder if music is also stored as ones and zeros. I wonder if movies are also stored as ones and zeros. I wonder if Gmail is stored as ones and zeros. I wonder.